So taking a look at our calendar, 34th class, the Rainbow Project is due. Throw it in the folder now for me. Wait, there you go.
Sorry.
There you go. All right, so throw the Rainbow Project in the folder for me. I have not created the regression project yet. I'll get it back to you as soon as I have it. Today we are covering something called L'Hopital's rule. On Friday is our review day for test number 3, which is on Monday. Okay, so this test coming up is on Monday. It's on everything in packet 3. This is the last day of new material for that test. Just looking ahead, after test number 3, we have 4 more days of new stuff. Then we've got a review day. This TBA is probably just going to be another review day, but I like to build in a possible snow day in case the weather disagrees with our calculus class. And then the final exam is coming up pretty soon. Where to go? Final exam, December 20, Wednesday. Yeah. Okay, there is one more project that I will hand out in a couple of weeks, but it is not a math project per se. It's just an opportunity to reflect on the semester. Questions on the calendar? Okay, so here we are on page 45. In this class, we use L'Hopital's rule to evaluate certain kinds of limits. So first, a brief history lesson about this guy. I don't know French. That whole thing is his name. Largely lived in the 17th century. He was a French mathematician who wrote the first textbook on calculus. Now you can see the word wrote is in quotation marks. Here's what happened. Back when L'Hopital was alive, very few people in the world knew this subject that we call calculus. Calculus was discovered in the mid-17th century. And so just a small handful of people knew how to do calculus, including the very famous Bernoulli brothers you might have heard of from lots of different places like physics. And so what L'Hopital did is he said, well, I need a tutor. This calculus thing is all the rage, and I want to learn how to do it. So I'm going to pay Bernoulli to teach me calculus, but they didn't live anywhere near each other. So really what Bernoulli did was just wrote a bunch of lessons about calculus, like essentially a book explaining this new field of mathematics. And he mailed it over to L'Hopital, who promptly put a cover page on this book and put L'Hopital's own name on it and said, hey, look at what I just wrote. And here we are. By the time that, so Bernoulli didn't say anything because he said, well, I was paid for my work, so I guess this is what happened. L'Hopital passes away, and then Bernoulli comes out and says, hey, this is my work, but the name L'Hopital's rule had already, it stuck. So here we are. So Bernoulli's rule today. All right, full disclosure, we aren't going to be making heavy use of L'Hopital's rule in Calc 1 or Calc 2. It will be on the test and the final exam, but it's really not going to pop up again after this. Okay, let's find the following limits. So we haven't talked about limits in many, many weeks. The very first thing to try when you have a brand new limit is to just plug in. So let's plug in x equals 1 everywhere we see an x. Okay, so what do we get upstairs? -3 over downstairs. 6. -1/2. That's it. That is the answer. That is the limit. It is done. We are going to talk about fancier limit techniques than that, but that is always the very first technique. When you see a limit, just plug in and hope that you get some single well-defined number. Okay, let's take a look at B. Brand new limit. What's the first thing we should do? Plug in. So let's plug in x equals 2. I'm going to do this on the side here. When I plug in x equals 2, we get 3 times 2 squared minus 2 times 10, minus 10 over 5 times 2 squared plus 3 times 2 minus 26. What do we get on top? 0. 0 is okay. What do we get on the bottom? 0. That's not okay. So you cannot just say the answer is 0. You also cannot say the answer is undefined. 0 over 0 means actually the answer could be anything. It could be 15, it could be negative pi, it could be anything. It gives us no information other than there is more work for us to do. So 2 techniques, one of them old and one of them new. So here's the old technique. This equals a limit as x approaches 2. I am going to factor the top and the bottom independently of each other and just see what happens. So this is now old kind of factoring algebra stuff for us. So 3x squared, there's only one way to build that. It's going to be a 3x and an x. And then we have to build a 10 in the other two blanks. Now, unfortunately, we have to build a negative 10. And unfortunately, there are several ways to do that. I'm going to write a bunch of them. Don't write this down. But it could be, for example, negative 10 and positive 1. Or it could be positive 10 and negative 1. And that's going to be completely different. Or it could be positive 5 and negative 2. Or it could be negative 5 and positive 2. Are there any other possibilities? Don't I have to switch? Like couldn't I put the 10 in the other parentheses? And it changes everything. And so there are 4 possibilities there, plus the other 4 that I didn't write. 8 possibilities. You need to find the one that gives you this minus x in the middle, and that minus x is supposed to come from doing the outers and the inners, these ones here, okay? Only one of them is going to give us a minus x in the middle. Okay, so this is like a lot of trial and error. Is the winner on the page right now? I don't think it's any of those 4. Like if you do outers and inners for all of these, none of them works. Yeah, Phelan? Oh, it is on this one here. 5x there minus 6x. Oh, good. All right, so we do have the winner on the board. Again, I'm such a wonderful actor. I have no idea whether or not my mistakes are on purpose. All of them are on purpose. So if none of those worked, you'd have to write the other 4 possibilities as well and pick the one that works. Okay, well, the point is that it's annoying, like factoring there, especially with the 3, makes it a little bit tougher. All right, let's get the answer for the other one, 5x squared. 5x squared plus 3x minus 26. Okay, 5x there, x there. Trying to build the 26. Again, there's a few possibilities, 26 and 1 or 2 and 13. All right, so I'm just going to, I don't know, what are we going to do here? 2 and 13. So I think we can do a 13 here and a 2 here and a plus there and a minus there. That is the one that works. If you do the outers and inners, outers is negative 10x, inners is positive 13x. That works. That gives us a positive 3x. But there are 7 other possibilities to try. I'm just telling you what the one is, but like I've hidden the fact that there's work involved in finding this factorization. But once we factored, we recognize that we can tell that there's something that's the same on the top and the bottom. What is that? X minus 2. So we can just straight cancel the x minus 2 on the top and the bottom. So this is kind of a mess. I'm going to rewrite it. Limit as x approaches 2. All that's left is 3x plus 5 upstairs and 5x plus 13 downstairs. Okay? So some fairly annoying algebra involved in getting to that spot. But now that we've got that spot, we have a brand new limit. And so we plug in, right? We just start the process over. You plug in x equals 2 and you hope you get something good. Upstairs, 11, downstairs, 23, 10 plus 13. So 11 23rds, that is the answer. That is the value of this limit, okay? That is old. And I want us to like struggle and recognize how annoying all of that factoring is so that we can appreciate the new L'Hopital's rule. Let's try the same problem again. Of course, we had better get the same answer, but in a different way. Or, okay, I'm going to copy the original as it is. Okay, and we are going to apply this brand new rule. Here's what the brand new rule says. It says that instead of doing the limit in its current form, we are allowed to do the following very strange calculation. You are allowed to take the derivative of the top and put it on top. And you're allowed to take the derivative of the bottom and put it on the bottom. And I'm not saying take the derivative of that whole thing, because that would involve what rule? Quotient rule. That's not what I'm saying. I'm saying separately take derivatives of top and bottom. So upstairs, what is the derivative? 6x minus 1 over downstairs, 10x plus 3. This is not the derivative of that fraction. Some of you have lost points for trying to take derivatives of fractions this way. This is like the freshman calculus dream, that you don't have to ever do the quotient rule. You can just do this. So I'm not like changing the fact that you still need the quotient rule, but this is not the quotient rule. And let's just see what happens. We have a brand new limit. What do we try? We plug in, so let's plug in 6 times 2 minus 1 over 10 times 2 plus 3. What do we get? 11 over 23, right? It's crazy. How does that happen, right? Like, it's just like you take these derivatives and somehow magically you get the exact same answer. Which technique was easier, the factoring or the magical derivative way? The magical derivative way. Thank you, L'Hopital, for paying Bernoulli to figure this thing out. Like, that's L'Hopital's rule. We're going to use some very non-standard notation here. This is EN notation. I would love for you to just put an LH above that equal sign to tell me that you are doing L'Hopital's rule. There isn't a standard way to indicate that. So this is your way of telling me I know what I'm doing. I'm applying L'Hopital's rule right here. Okay, so L'Hopital's rule applies in a very small but useful collection of limit cases. One of them is this one right here. If you see 0 over 0, you are welcome to use L'Hopital's rule. However, you cannot just use L'Hopital's rule for every single limit. For example, you don't need to write this, but I'll do this one real quick. What was the right answer for this one when we just plugged in? -1/2. Let's suppose we didn't plug in and we just said, oh, it's a limit question. Clearly, Ian wants me to use L'Hopital's rule. Let's try doing the L'Hopital's rule thing. Don't write this. Equals L'Hopital's rule. Limit x goes to 1. Okay, so separate derivatives upstairs. 4x cubed plus 2 downstairs. 14x minus 4. Okay, let's plug in. It's a new limit. Let's plug in x equals 1. What do we get upstairs? 6 over, what do we get downstairs? 10. Is that the right answer? It is not the right answer. You cannot just willy-nilly do L'Hopital's rule on every single limit you see. It's a small class of limit calculations for which it works. 0 over 0 is one member of that class. There's another member we'll see on the next page, okay? 0 over 0, L'Hopital's rule. On the next page, let's try this guy. This is a limit when x is approaching infinity. It doesn't make sense to say just plug in because infinity is not a number that we can plug in. That said, we do have a theorem from maybe back in pre-calculus that tells us how to handle horizontal asymptotes. You guys remember graphing horizontal asymptotes for rational functions? In this case, the power on the top, the degree, the highest power, is 2, which is a tie for the highest power downstairs. So 3 over 5 is that's the answer to this problem. This limit is 3/5. That is the easy theorem from pre-calculus. It's just straight up 3/5. But really, that calculus, the pre-calculus theorem, comes from someplace reasonable, which I typically don't ask my students to do. But I'll just show it to you one time so that you can see that it's kind of annoying, and then you can appreciate the new and improved way to do this. Okay? I can't do any better than just say, look at the coefficients of the leading terms. Like 3/5 is that's the shortest way to get the right answer. But that comes because we're just kind of hiding the actual work involved. So here's the actual work. I'm going to take this fraction, and I'm going to multiply top and bottom by 1 over x squared. That x squared is because that's the leading power. So let's see what happens when we distribute that 1 over x squared through top and bottom. So, yeah, you can write this down. Limit x goes to infinity. Okay, so when I distribute the 1 over x squared in the first term, I'm just going to get 3, right? That x squared is going to cancel that x squared. So we just get 3 minus. Now what happens here when I multiply these two guys? Like one of these x's is going to cancel this one, but there's still going to be one of those x's left from the x squared on the bottom. And then the last one is just minus 10 over x squared. Nothing to do there. Take a moment, see if you can do the same kind of calculation on the bottom. Distribute that 1 over x squared. Yeah, the powers end up getting reversed. Okay, and now we are going to send x to infinity. And we're going to make use of the following fact. If you have, where is it? Here we go. Any finite number divided by infinity is basically 0. By that, 17 divided by some massive, massive number approaches 0. And that's what we have up here. We are going to take a look at, for example, this fraction right here. When x gets really big, x is going to infinity, I have 10 over a massive thing. What does this fraction head towards? Heads towards 0. Then I have 1 over x. 1 divided by something really massive also heads towards 0. This 3 doesn't have any x's in it, so it is entirely unmoved by the x going to infinity. So the numerator approaches 3 minus nothing, 3. And the denominator, what happens to the 26 over x squared when x gets really big? That one goes to 0. The 3 over x goes to 0. The 5 is just 5. So the answer is 3/5, which of course is the leading coefficients. But that's why it's the leading coefficients, is because all of the other things other than the leading terms end up going to 0 when you do what we really should do, which is this division. Okay? So that's the annoying way. But let's try the new way. So the new way is L'Hopital's rule. So let's copy it again. Or limit x goes to infinity. I'm just copying that guy from up there. Okay. It appears that if we plug in x equals infinity on the top, let's see, so there's like 3 infinity squareds minus an infinity minus 10. Do you see who's winning? Is it like the 3 infinity squared, or is it the minus infinity? 3 infinity squared, right? That infinity squared is getting bigger much faster than the minus infinity is trying to pull us down. So, I mean, the top is dominated by the leading term, and so is the bottom. So the top and bottom both are going to infinity. Infinity over infinity is the other fundamental thing that L'Hopital's rule works on. 0 over 0 we saw on the previous page, infinity over infinity we see here. You are allowed to use L'Hopital's rule in those two cases. So let's try it. We'll put our little fancy LH. We'll copy the limit. And then we will do our derivatives separately, not the quotient rule. 6x minus 1 over 10x plus 3. And we have a new limit. And so we kind of plug in, but it's tricky because it's infinities. But what's happening to the top when x gets really big? That goes to infinity, right? 6 times something massive minus 1. And how about the bottom? It's also infinity. So again, we are infinity over infinity. It seems like we haven't made any progress. You know what we're going to do? You could do the 1 over x trick here, right? The thing that we did, like the pre-calculus thing. You guys know the Eagles, the band? Art says the best line in any, best calculus-inspired line in any Eagles song. Take it to the limit one more time. That is what we're going to do. It is infinity over infinity, right? So we can do L'Hopital's rule. So upstairs, so we get another LH here. Limit is x. You didn't realize that song was about limits, but it is. So what's the derivative upstairs? 6 on the bottom, 10. No more x's. It's just a plain old fraction, which is the right answer of 3/5. Okay? OMG. All right, so looking at the summary down at the bottom, some basic limits that will prove useful. You're going to do a lot of this stuff in the activity. If you have 0 divided by any number other than 0, like 0 divided by 17 or 0 divided by -5, it is just plain 0. It is not L'Hopital's rule. It's 0 and the problem is done. If you have something that looks like any finite number over either infinity or minus infinity, like 17 over something massive or 17 over something negative and massive, both of those are heading to 0. It's not L'Hopital's rule. It's just 0 and it's done. The other direction of this first one, if you have any finite number over 0, like 17 over 0, That is straight up undefined. It is not L'Hopital's rule. It's undefined. The answer is probably better than saying undefined or doesn't exist. Probably more informative to say infinity or minus infinity. I'm imagining something like this. And so like if I said, hey, what happens to this function as x approaches 2 from the right? Well, it goes to positive infinity. And what happens is if x approaches 2 from the left, it goes to negative infinity. Like that's saying more to the reader than saying, oh, it just doesn't exist and let's not worry about it. If you have plus or minus infinity over any finite number at all, that's just plus or minus infinity. You have to check the signs. And then as we said, 0 over 0 and any combination of infinities with pluses and minuses, that's what L'Hopital's rule applies to. Anything else is not L'Hopital's rule. Okay, so the activity is on the next page. I will walk around.